Hello friends. Now in the previous discussions we have learned about the basics of distillation, then methods of distillation for binary system, and in the previous presentation we have discussed about the simple or differential distillation. Now in this presentation we are going to discuss about the flash or equilibrium distillation. The contents for this presentation are the flash or equilibrium distillation setup and their explanation, then material balance equation for the binary mixture or the derivation of operating line, and then the derivation for the material balance and their implementation in terms of XY diagram. So we can draw the different operating lines on the equilibrium diagram for different conditions. So the learning objective for this presentation is that students should answer the following questions like drawing the diagram, explanation about the flash distillation, then derivations of operating line equations, and plotting the operating lines for the different conditions on the XY diagram. Now in the previous presentation we have already discussed about the distillation ways. So generally there are two ways of distillation process, that is distillation without reflux and distillation with reflux. So in the previous case we have discussed about the simple or differential distillation under distillation without reflux. Now in this case we are going to discuss about the second example, that is flash or equilibrium distillation. So let us discuss in detail what exactly this flash distillation is. So in this experimental setup we can understand there are three components, that is heat exchanger, PRV, that is pressure reducing valve, and separator or column. So in this method we are going to feed this liquid component mixture through the heat exchanger, where this heat is gained by these liquid components, and after reaching the bubble point it is going to change into its vapor. If the heated liquid is gone through the PRV where the pressure is going to reduce, then due to the reduction of pressure these liquid components are converted into flashes. So these partially vaporized components are going to separate from the top of the column, and remaining liquid can be separate from the bottom of the column. So this is a separator. So to separate these vapors and to separate these liquids we are using this terminology as a separator. So in this case you can understand that more volatile components are there in the vapor phase, that is on the top of the column, because they are having the less boiling points, and if the less boiling point is reached first, so obviously the MVC rich components are separated on the top side. So that is in terms of vapor. And when the MVC or the majority of MVC is separated from the top, then remaining things are majority is LVC. So liquid residues are rich in LVC and the vapors are reached in MVC. So this is a simple process, and why it is called as flash distillation, because when this feed or these liquid components are having the high temperature due to the heat exchanger, and reduction in the pressure, and due to this high temperature and reduction in pressure, these liquid components are converted into flashes. So this converted into flashes, that is why it is called as flash distillation. And after converting these liquid components into partial vapors and partial liquids, then in the separator or in the column, these vapors which are produced and the remaining liquid are in equilibrium, and that is why this process is also called as equilibrium distillation, right? So for the material balance equation, we can understand that this feed is an input, so we can assume this feed as a binary mixture. For the simplicity, that is the combination of MVC and LVC or A and B, and we can assume that this feed as 1 mole. So after feeding this 1 mole feed through the heat exchanger and PRV, then in the separator they are going to separate into the vapors and liquid. So these vapors which are generated can be indicated as F, small f, and the fraction for this F is small y. As it is in the vapor phase, that is why the mole fraction of MVC in terms of vapor phase is indicated by small y. And the feed is in liquid phase, that is why the fraction of this feed can be indicated by XF. Then the remaining liquid can be indicated as 1 minus F, because 1 is feed, F is vapor, so obviously 1 minus F is nothing but the residual liquid, and the fraction for this liquid is small x. So X indicates the mole fraction of more volatile component in liquid phase, that may be in the residual liquid or that may be in the feed, and the mole fraction of MVC in vapor phase, that is indicated by small y. If we assume the overall material balance for this separator, then we can consider it as input is equal to output. That is the basic equation of mass balance. So input is feed and the outputs are vapor and residual liquid. So feed now we assume as 1 mole and the vapors are F and the liquid is 1 minus F. And for the individual material balance of more volatile component, we can write this material balance equation in terms of individual material balance. So from this diagram, we can write the individual material balance for MVC. So again, MVC in feed, that is equal to MVC in vapor plus MVC in liquid. So MVC in feed, it means the feed moles, that is 1 into fraction. So here fraction is XF. Then MVC in vapor means F and fraction is Y, and MVC in liquid, it means 1 minus F and fraction is X. Then in the next step, we can rearrange this equation as F into Y equal to XF minus 1 minus F into X. Then again rearranging this equation as y equal to xf upon f minus 1 minus f into x upon f. So this is the material balance equation or operating line equation for the flash distillation or equilibrium distillation. If you compare this equation with the equation of straight line, that is y equal to mx plus c, then you can understand this is y, this is mx. So the slope is minus 1 minus f upon f. So slope of this operating line of flash distillation is minus 1 minus f upon f. So with the help of this slope, we can calculate the slope for the different conditions, and then we can plot the operating line on the XY diagram. Okay. So let us discuss the different conditions. So as you know the final equation now, and even the slope also. So if you write the final equation, that is y equal to minus 1 minus f x upon f plus xf upon f. This is the final equation. And if you consider the point of intersection of the operating line and the diagonal, because if you see the x versus y diagram, that is equilibrium diagram, on this case the diagonal indicates x equal to y condition, right? So for drawing the operating line, we must have the point which is placed on the diagonal. So that is nothing but the intersection or the point of intersection of the operating line and the diagonal. So this is the point. So that point should be clear first. So let us obtain that point first. So we know that on the diagonal y equal to x. So we can replace this y as x, then 1 minus f into x upon f plus xf upon f, right? So this is the denominator, that is f is common, can be taken on the left hand side. So f into x equal to minus x into 1, that is minus x into minus f, that is plus xf, and then plus x suffix f. So this fx and this fx gets cancelled, and we get x equal to xf. And we know that this y is equal to x condition is there. So we can write y equal to xf. So x equal to xf and y equal to xf. So this is the point of intersection of the operating line and the diagonal. So here we can write as x equal to xf and y equal to xf. So this is the one point to draw the operating line of flash distillation, and in the same way we can understand the other conditions. Suppose if the f equal to small f equal to 1. It means whatever the feed is there, 100% feed is converted into vapors. So if that is the case, then what will happen? So if f equal to 1, we know that the slope of the operating line is minus 1 minus f into x upon f. We are concentrating on slope only because now we get 1 point for drawing the operating line. If you know the slope of the line, we can draw the operating line now. So for f equal to 1, put this value. In the slope equation, so we get the value as minus 1 minus 1 upon f. So that is 0. So when f equal to 1, slope is 0. So if the slope is 0, it means it is parallel to x-axis. So this is the case where we can show that this is the condition of f equal to 1, parallel to x-axis. As slope is 0 means no slope is there, it means it is parallel to x-axis. Then another case is if f equal to 0, then slope becomes minus 1 minus 0 upon 0. So anything upon 0 is infinity. So slope is infinity, it means it is parallel to y-axis. So this is the line. So we can write here that this is the condition where small f equal to 0. And if the value of f is in between 0 and 1, then there will be certain value in between 0 and 1. So this is the condition, that is f is less than 1 and greater than 0, right? So this line may lies in between these two lines, that is parallel to x and parallel to y axis, right? So these are the different conditions of flash distillation where f can be 1, f can be 0, and f can be between 0 and 1. So on the basis of f values, we can calculate the slope of this operating line, and on the basis of this slope, we can draw the operating line on the XY diagram, right? So generally, the operating line of distillation is like this, and then you can draw the operating lines with the help of this flash distillation conditions, right? In case, suppose in some of the numericals, they are asking about the data, that is composition on the XY diagram, that is the point of intersection of this operating line and XY diagram. So we can easily identify this from this point of intersection. So this is the value and this is another value. So it may be indicated as x1 and y1. So we have to identify the condition, then we have to calculate the slope, then we have to calculate the angle for the operating line, and then where it is intersected with the XY diagram, that point indicates the x1, y1 values, that is nothing but the mole fractions or the compositions for that particular condition. Okay, thank you.